Well, good afternoon, good morning, good evening, depending on where you are. This is Craig Maddox, I'm CTO of Moberg Analytics. I'm joined by Dick Moberg, our CEO and founder, and Ethan Moyer, our VP of R&D. We are fresh back. Well, Ethan and Dick may not be super fresh because they took a red eye back from San Diego last night. We are fresh back from the Neurocritical Care Society annual meeting in San Diego, and so we are very energized. It's always a fantastic meeting, and we saw lots of old friends, saw lots of great technology, learned a lot, and made some great connections, and got a chance to show our cloud and clinical platforms, and it was a great show. We had a fantastic time. So welcome to the 12th edition of the Case Studies in Neurocritical Care AI webinar. Just to remind you kind of why we're doing this, we understand that treating brain injury is a gigantic mission, and our goal when we founded this company is to help in that mission. That's with providing tools and products, but also to do things like this webinar series. So enable you on your way to using AI and using the data that's become available and accessible to help advance the field. So we do things like the webinar series. We have starter grants to provide infrastructure for bringing your own problems, AI problems to the cloud or on premises. So that's why we're doing this. Reminder to please provide feedback. These, we want these to be useful. We want them to help you along your journey. So if you have suggestions for improvements, if you have suggestions for topics, or importantly, if you want to volunteer to speak, we see so much. We go around to poster sessions and we see so much incredible work, and we would love to highlight that. Some people on the call that I see out there have graciously taken advantage of that. So please let us know if you want to present something. Here's a list of the past 11 sessions. The replays are all available via our website at that handy link down there. So you can go back and catch up and see some of the other really cool topics that have been presented. Also, if you have not yet received an invitation, you should have received an invitation to have a look at the clinical cloud platform on using some of the data we've received from the Boost 2 team, so you can go on and kind of try things out. Please let us know if you want to do that and you should have received that invitation. If you have questions, please use the handy Zoom Q&A feature located on the menu. So we usually we go far and wide to find speakers for our topics. We didn't have to go very far to find a really great and interesting speaker today. Tony Okeke is a machine learning engineer here at Moberg Analytics. He recently graduated from Drexel's accelerated bachelor and master's program in biomedical engineering. He's got a background in data science, machine learning, bioinformatics. He's got experience both in academia and at pharmaceutical research. He did that at GlaxoSmithKline, and he worked at Penn as well. His work here at the company focuses on applying AI to the analytics and interpretation of neurophysical data. Recently, he's been doing a lot of work with automating artifact detection for ABP data. And so today he's going to talk about that. He's a fantastic guy, a great educator, and we're really excited to have him show some of what he's been doing. So with that, Tony, I will stop sharing and let you take it away.
Thank you for the introduction, Craig. Let me share my screen. Okay, so today, like Craig said, we're going to be going over automated artifact detection, specifically for arterial blood pressure data. And we'll be covering models ranging from simple heuristics to different deep neural networks. So when patients are being monitored in the ICU, you're collecting tons of different modalities, tons of higher resolution waveform data. And the figure here kind of shows that you're doing this across 30 different devices, and a lot of them are collecting multiple modalities. All of that data gets aggregated either in the ICU room itself or within the hospital network or uploaded to cloud providers for analytics. Artifacts appearing in this data can take the form of different forms of distortions that obscure the actual physiological signals that we're interested in. And the challenge with this is it makes it very easy to misinterpret the signals that we're looking at. These artifacts can be caused by a wide variety of things. So if a patient is moving around, if there's interference from some of the other instruments in the ICU room, or if there is medical interventions that doctors are performing to save the life of the patient, all of these things can contribute to artifacts appearing in the data set. And here we have an example of a recording from a patient who is in the ICU. This is arterial blood pressure data. This recording segment is about a minute long, and you can see here that there's a very clear artifact where the blood pressure value spikes to over 400 milligrams of mercury. In this case, it's very easy to identify this kind of artifact because it's obviously not a regular blood pressure pulse. And you would think you could just simply apply a rule that says if blood pressure is above a certain threshold, we can just exclude that data. But there's also cases where artifacts can be more subtle and it can be harder to detect disturbances in the data set. This becomes challenging because when a patient is in the ICU for an extended period of time, you're collecting hundreds of hours of monitoring data across dozens of different modalities. So it's not feasible to manually go through and annotate the data and extract all of those different artifacts. These artifacts can have a negative impact on patient care because it can lead to a misinterpretation of physiological signals, where if someone who's less experienced is looking at some of this data, it might be harder for them to identify that a piece of data is artifactual or if it's normal. And as is increasingly the case, we're processing a lot of this data using machine learning models. And these models are often sensitive to differences in the distribution of data that they're being fed. So if there's artifacts that don't represent a real blood pressure signal, machine learning models and other algorithms that have been tuned to work on that data will misclassify and show other performance bugs. So for today's session, we're going to be going over implementing some different methods for doing artifact detection. And we'll start off by just going over the different packages that we're going to be using. Pandas, NumPy, SciPy, these are all pretty standard for different data science tasks. These will help us with manipulating data, doing numerical computing, and any of the digital signal processing we're dealing with. Matplotlib is going to cover the data visualization. Scikit-learn is a package that provides a toolkit for general machine learning. It has out-of-box implementations for traditional machine learning algorithms, and also provides a bunch of tools for doing model selection and evaluating these models. We're also going to be using PyTorch, which is a library that is dedicated to building, training, and evaluating deep neural networks. And it's particularly optimized for GPU-accelerated environments. Often, when you're training large deep neural networks, you typically have to parallelize that across multiple GPUs, and PyTorch makes that very explicit and easy to do, depending on whatever architecture that you're working with. We're also going to be using Rich, which is a library I like for formatting outputs. And finally, we're going to be using the CNS utils package, which is something we've developed internally here at Moberg. And it effectively allows us to load and process high-resolution waveform data using very convenient timestamp indices, so that way you wouldn't have to load in 100 hours of recording data to find the segment you want. You can just specify the timestamps and extract that, and we'll see an example of that shortly. So just starting off by loading some of the packages. One other thing, we're going to be using data from the track TBI cohort. Specifically, we have ABP recordings from one patient that we're going to be using to evaluate and test some of the different models. So let's start off by loading some of this data. The first step with using CNS utils is creating this CNS data source object. And essentially what it does is it creates a nice wrapper around the CNS archive that makes it easy, that gives you tools for extracting that timestamp-based data. Here, we're going to actually extract out a chunk of data from this patient. And the way it works is you first create a data reviewer that is specific to the modality you're interested in analyzing. You can then specify the specific timestamps that you want to extract from the CNS archive. And in this case, we're using Pandas timestamp objects because it provides you a convenient way to go from a string that specifies the date and time to a numerical timestamp. So, the reviewer object expects timestamps in microseconds, and Pandas stores these values as nanoseconds. So we're converting them first to microseconds by doing this division here. And then we are passing that to the review data function. And what that does is it reads the section from the CNS archive that we're interested in and returns a Pandas series where the index represents the individual timestamps for each data point, and the values in that series represent the ABP waveform in this case. Oh, my bad. So let's take a look at what this data looks like. Here I'm plotting out this segment, and as you could see previously, I am taking out a segment of about 2 minutes. And here you can see there are two big regions where there's clearly an artifact. There's something weird going on in the data set. And we can kind of look into that and see what's going on a bit more clearly. Here we're defining another set of timestamps, and we're creating an index that we can use to extract out that specific region. It's about 30 seconds from the data frame that we extracted. And you can see here there's these spikes that aren't representative of a natural blood pressure signal. These could have occurred due to a variety of factors, like we mentioned earlier. Maybe the patient was moving around, or the doctors had to administer some medication. But regardless, this is an artifact that we want to identify and remove from the data before we move forward with any other processing. Before we can get to actually running any of the models, we have to break up this large waveform data into more easily processable chunks. So because our end goal is to train deep learning models on this, we want to split the data up into individual pulses that we can then use to train the deep learning models. And the way we're going to do that here is first by segmenting the data into small 5-second pulses or segments. And then from each of those segments, we can extract out the individual pulses. The reason we do it this way is because when you're processing hundreds of hours of data, if you can split that up and make it easier to parallelize that across different GPU nodes, for example, that will make your pre-processing run a lot faster and save you a lot of time in getting the data ready for the models you're going to train. So the first step in doing this is calculating the sampling frequency. And we have this function implemented here where essentially it takes the timestamps from the data frame index, extracts out the first 10 seconds of the recording and converts those from nanoseconds to seconds. And then we calculate the interval between those timestamps and take the inverse of the average interval to get the average sampling frequency for that segment. And here you can see it's about 125 hertz. Next, we need to split the data up into the segments that I mentioned earlier. And here we're going to be using 5-second segments. So the first thing we need to do is calculate how large each of those segments are. And that's as simple as taking number of seconds times the sampling rate. So we're going to need 624 samples for each of these segments. Next, we can loop through the original data frame. So this for loop here is going through each of the different, it's going through from the first index in the data frame through the last with a step size equal to the segment size. And what we're doing is we're extracting out segments based on that segment size. So it's effectively a sliding window through the waveform data. And we extract out 25 different segments. Next, we can start to visualize this and see exactly what the individual segments look like. And here you can see this is a pretty standard ABP pulse. We have another one here that includes some of that artifact that we noticed earlier. And here, the next thing we want to do is actually extract out the pulses from that signal. So to do that, the first thing we are going to do is apply a Gaussian filter to reduce the noise in the original signal. Then we will apply a fairly simple algorithm to identify the peaks and troughs in that signal using SciPy. And based on the indices for those peaks, we will extract out the individual pulses. We're also going to use a parameter to make sure that the pulses are about 0.4 seconds apart to make sure that we're accurately separating out the pulses. So this function here implements what I just talked about. We're first starting by applying that Gaussian filter to get rid of the noise. And then we take the inverse of the signal so that we are finding the find peaks function is designed to find the local minima. So we take the inverse first, and then we pass that distance function. And this gives us the indices for the different peaks that appear in that signal. And in running that, these are the different indices that it identifies. And here we can extract out the individual pulses. So what we're doing here is we're going through each of these indices, and we're taking the region between, say, 46 and 98 and storing that as a pulse. And then we're just moving through all of the indices and extracting out the pulses. And here you can see that once we plot out that signal, each of the different pulses is given a different color in the plot. So you can see we're correctly identifying the start and end points for each of the blood pressure pulses. After doing this, the next step is annotation. And this is probably the most important part when you're developing any kind of machine learning model. You need high quality annotations to make sure that your models are actually learning the ground truth of the data you're trying to represent. And in our case, we had a team of clinicians go through and annotate a small segment of the data that we extracted from the track TBI patient. And we're going to be using that segment of data for evaluating the models that we discuss in subsequent sections. But before we go into actually training any of the models, I wanted to give an overview of the different metrics that we're going to be using to assess their performance. There's 4 metrics that we're going to be interested in here. Accuracy, which, as the name suggests, is the proportion of correct predictions that your model outputs out of the total number of samples that you tested on. So you want a really high accuracy, but accuracy alone is not enough to gauge the performance of the model, because if your data set is unbalanced and you have different numbers of one class over the other, accuracy doesn't sufficiently quantify how well the model is discriminating those classes. Because of that, we're also including sensitivity and specificity. Sensitivity is the proportion of true positive cases. So in our case, it's a proportion of artifacts that the model correctly identifies as artifacts. While specificity is the proportion of actual negative cases or true negatives. That's the number of non-artifact pulses that are correctly identified as non-artifacts. In our case, we really care about sensitivity because we want to make sure that when the model says a pulse is an artifact, it's very certain that that actually is an artifact. That way, when we're excluding those pulses from our downstream analysis, we're reducing the chance that we discard useful data. The last metric, F1 score, is a balance of, you can think of it as a score that kind of balances sensitivity and specificity. The higher it is, the better the model is at identifying true positives and minimizing false positives and false negatives. It's a good metric to use when you have an unbalanced data set. And in the code that I'm going to show you, I'm using a function evaluate model that effectively is just a wrapper around some scikit-learn functions for calculating each of these different metrics. So the first approach we're going to talk about for identifying artifacts uses simple clinically informed heuristics. These are just basic rules that we've identified based on conversations with the clinicians that we're collaborating with. And these rules are pretty good at identifying whether or not something is an artifact. The first rule is the minimum value threshold. So an ABP pulse is never going to be below a certain number, because if that were the case, the patient's probably dead. Maximum range and minimum range basically say the distance from the crest to the trough of the ABP pulse can't exceed a certain threshold and can't be below a certain threshold. And finally, the number of peaks says if a pulse has more than a certain number of peaks, then it's probably not real. All of these are based on kind of what is physiologically reasonable for a patient to exhibit, but the exact threshold values we determine through a process called grid search, where we put in a bunch of values that seem physiologically reasonable for each of these different thresholds. And then we evaluated the performance of a classifier that uses all 4 of the heuristics, using every possible combination of those numbers. And then we pick the set of numbers that gives you the best classification accuracy effectively. And the numbers shown here are the results of that grid search process. So now we can actually get into implementing some of this. The code is fairly simple. Each of these functions basically looks at, the first function is it calculates the mean of the minimum value of the pulse and compares that to the minimum threshold. We're using PTP, which stands for peak to peak, to calculate the range between the crest and trough of the pulse, and then comparing that to the minimum and maximum range. And then we're using find peaks to determine the number of peaks. To actually create the classifier, we're basically taking a combination of all four of these rules. So if any of them says that a particular pulse is an artifact, the classifier will output a true, indicating that it's an artifact. So next, we can actually run this on some of the data. So this code here just loads the pulse data file. There is, because of the way the pulse data is stored, it includes the actual waveform data in the CSV file. So I have a function that reads in the data from the CSV and puts it into a nice pandas data frame that we can use for all of our analysis. We have a label that indicates whether or not it's an artifact. So 1 is an artifact, 0 is a normal pulse, and then we have the actual pulse data. Next, we can run the model on this heuristic model on the data set. And what we're doing here is we're extracting out the true labels from the data set, and then we're just looping through all of the different pulses and adding the predicted values to this list. We can then pass those values to the evaluate model function, and that'll give us an output that tells us the accuracy, F1, score, sensitivity, and specificity. You can see that this model does not really perform well. The accuracy and F1 score are pretty low. It is 100% sensitive though. So what that tells us is even though these heuristics aren't good at identifying, say, a normal pulse from an artifact pulse, it is good at identifying only artifact pulses. So in as much as it's not a general purpose classifier, it does have some utility in that it can correctly identify the artifactual pulses. So the next thing we're going to look into is deep learning models. We're going to be looking at two different approaches. The first is a combination of a stacked convolutional autoencoder with a convolutional neural network. And the second uses a pre-trained image classification model that we fine-tune for this task. That's a lot of jargon, and I will go into more detail on the next couple of slides. But before getting there, I wanted to give you a brief overview of the dataset object in PyTorch. This is a pretty important abstraction that PyTorch provides, and it's effectively a way, it is a Python class that you can use to create custom datasets. So depending on the kind of problem you're working on, you're going to need to do different transformations and pre-processing to get your data in a state that it is ready for the deep learning module. The dataset class effectively allows you to write all of that logic and encapsulate it in a Python class, and then pass that to a data loader, which will automatically handle combining those samples into batches for training the deep learning module and optimizing that to run on GPUs or whatever compute configuration you are using. So we are going to implement a custom dataset that takes the raw pulse data and converts it into 2D arrays. The reason for this is both of the models that we're going to be working with are image-based, so they expect inputs in the form of 2D arrays. And the code here goes over the implementation of this dataset class. In general, any PyTorch dataset will include 3 functions: an init, length, and getItem function. The init function is what creates the data set in the first place. So it will handle loading the data in from whatever file you're using and storing any configuration options. So here, the first thing we're doing is checking to make sure the file actually exists, so you don't waste time reading data that's not there. We load the pulse data, and we define some parameters that become important for the different model architectures we're using. We're also defining a set of transforms. So one thing that's very common in PyTorch when you're working with image models is applying different transformations to get your data into the right state before you pass that off to the machine learning model. The first transform here just converts the image from a NumPy array to a pill image. Pill stands for pillow. It's a fairly standard format in Python for representing images. And then the rest of this handles resizing and converting the image into a tensor, which is an equivalent to a NumPy array that can be moved back and forth from CPU to GPU. The length function is self-explanatory, and getItem is what actually handles reading the pulses from the data set. So you pass an index that you want to retrieve data for, and this method will extract out that specific index from your data set. And in our case, we're just reading out the corresponding row from the pulse data frame, extracting those values, converting it into converting the pulse to an image using this utility function that I wrote. And effectively what it's doing is, because each of the pulses are of different lengths, this will interpolate them down to the same 64 points and then convert that into a 2D array. And then we pass that to the PyTorch transforms and return the final image and label. Here, we're just creating an instance of that class and using it to extract some data. One thing that's interesting is when you extract a single piece of data here, instead of just having a 64 by 64 image, you have 1 by 64 by 64. That first dimension represents the batch. In this case, because we're not using a data loader, it's a single training sample. But when you pass that through a data loader, what PyTorch will do is it'll collate a bunch of different examples into a batch that you can then show the model during each individual training run. And here we're just plotting out one of those representative images. Basically, these models, instead of seeing a single 1D array, they just see a plot of the pulses instead. Okay, now for the actually interesting stuff. The stacked convolutional autoencoder plus CNN. This model was initially developed by Lee et al. In a paper published in 2019. It combines two different kinds of neural networks, an autoencoder and a regular convolutional neural network. The autoencoder is specialized at learning to reconstruct data. So if you give it an image of a cat, the autoencoder will compress that cat down to a single vector of numbers, and then use that single vector of numbers to reconstruct the original image of the cat. And the idea here is when you do this, the output from that model contains a more generalized representation of the features from that image. You can then take the output from that model and pass it to CNN. A CNN is probably what comes to mind whenever you think of like deep learning image classifier. It basically takes an image and then uses a combination of different convolutional layers to compress that down into a smaller latent space that you can then use for classification. So you start off with like the original 2D data, and then it progressively gets compressed until you end up with one-dimensional representations that then get converted into classifications. In this case, either normal or artifact. And during training, we're going to be training both of these models together. So the autoencoder uses a loss function. Loss basically means error. It uses a loss function that measures the error in the reconstruction. The CNN uses a loss function that measures the classification error. So we take the average of these two, and then we propagate the error function back through the model during the training runs. This code kind of goes through an implementation of each of the different parts of this model. So first, the stacked convolutional autoencoder. You start off by defining your encoder and decoder parts, and the encoder is basically a convolutional layer that goes from your 64 by 64 image to a 32 by 32 image, and then down to a 16 by 16. And then the decoder basically expands that out back to the original 64 by 64 image. Here it outputs to 32 by 32, but when you output the final present prediction, it expands that back to 64 by 64. The forward function is pretty standard for all PyTorch models. This is what defines what actually happens when you make a prediction with the model. So you first call the encoder, so you pass the input through the convolutional layer, and then you apply an activation function to kind of normalize the output from that layer. Then we pass that to the pooling function. then to the decoder, and finally you get the output from the decoder. Next is the CNN, and here it's a similar setup where you have multiple convolutional layers that kind of compress the input progressively until you get to this flattened layer where you now have two sets of flat layers that are used to convert that image representation into a classification, basically. The last layer is what actually does the classification and outputs the probabilities that you can then use to determine which class the sample is from. And the forward pass here basically does the same thing, where we're calling each of these layers individually on the input data until we get an output signal. And finally, we can combine both of these in this much simpler class where we have the convolutional autoencoder and then the CNN, and you're basically just passing the input through each model and returning the output. So because training these models can take a while, we are going to skip that bit and we'll use pre-trained models. So the models that we're going to be using for the rest of the presentation were trained on a data set of 900 annotated pulses. And here we're going to be evaluating it on this smaller data set. So the first thing we do is create a data set. The SCAE model uses an image size of 64 based on its architecture, and then we create a data loader that will combine the samples into batches for training. We load the model, and then this bit of code here basically loads the weights from a .pt file, and this handles moving the weights from CPU to GPU because the model was originally trained on a GPU, and this just tells it to only load the weights. One other thing that's important is you have to put the model in evaluation mode because PyTorch does a bunch of things under the hood whenever you run a model. It calculates the gradients based on whatever input it's passed, and that takes up some computational overhead. So putting it in eval mode basically tells it not to do all of that. And now we can actually make predictions. So we have empty lists to store the true and predicted values, and then we're looping through the data loader. So each of these will give you a batch of 32 images, and then we put those 32 images through the model to get the predictions. And then I have a function here that converts, so that will give you a 2 by 32 tensor or array of all of your predicted probabilities. So this function will then convert those probabilities into, it will convert those probabilities into actual classes. And then we store that in YPred and store the true labels. We can then calculate the metrics for this model. And you can see this performs much better than the pure heuristic model. The accuracy is a lot higher, the F1 is a lot higher, but one trade-off that is very apparent is you do lose out on something like sensitivity, even though specificity in this case became a lot higher as well. Next, we're going to go over the ResNet 18 model. And here we applied something called transfer learning. This is a pretty common technique that's used in deep learning research, and it became popular in part because of this ResNet architecture. The idea is when you train a very large neural network on a lot of data, so in this case, we're using something called ImageNet, which includes over 1 million images. That model becomes a very good feature extractor that you can use for pretty much any image. And the idea is when you want to train a model for a more niche task where you don't have as much data, you can start off by taking a model that's been pre-trained on this huge ton of data and then continuing its training on your smaller data set. And the idea here is because it has already learned how to extract features from images, the additional tweaking that your data set does will tune the features it's extracting towards the problem you're working on without losing the knowledge that the model has already gained. So in this case, what we do is we take the pre-trained model and then we change the last 2 layers so that it takes a single channel input, and then we replace the last classification layer based on the 2 classes that we are interested in outputting in this case. And this is what the architecture kind of looks like for ResNet. It's basically a series of these convolutional blocks where each block talks to the previous block using some residual function, and that propagates the information that's learned in each of the layers back through the network. The model was pretty, what's the word? Revolutionary when it was first released, and it's been cited a bunch in a bunch of different papers and used for a lot of different classification tasks. This is a very good proof of concept for showing that transfer learning works, even when you're moving from the general case of image classification to something as niche as artifact detection, where we're not even using images strictly, we're using plots. And here we're just using the cross entropy loss because this model is just interested in optimizing for classification. Here is the implementation of this model. We're first loading the ResNet 18 model with the default weights from PyTorch. PyTorch provides this models object in the Torch Vision library that basically gives you access to dozens of different pre-trained models. We're changing that first convolutional layer to accept a single channel input based on our data set, and then we're replacing the final layer with a fully connected layer that outputs the number of classes we're interested in. And our forward pass is effectively just passing the input through the ResNet model. And like before, we'll skip the training step and go into just inference. We're doing the same kind of creating the data loaders and then loading the model. The only difference here is we're using an image size of 224 because when the ResNet models were trained, they were trained on images of that size. And here we're running the predictions the same as before. And you can see here, the performance is, I'd say, slightly better than the SCAE model. And I think this shows kind of the power of transfer learning because the models are already very good image classifiers. So it doesn't take much to optimize their performance for whatever task you're working on. I think the thing that's interesting here is that it actually works on the pulse data set. Yeah. And kind of just comparing the results from all of these models, table's a bit small. Yeah, so you can see the heuristic model kind of performed the worst, but it did have the best sensitivity of the models. And the ResNet model, I guess, performed the best on average across all of the different metrics. And this was just on the small test set of about 40 pulses from this one patient. And that covers it.
Thank you, Tony. I have one question. Can you shed light on how the SAE CNN model was trained? What data went into it to train it?
So we're using data from the Precise Cap study. We have, excuse me, we have 900 pulses that were annotated by a team of clinicians to identify them as either artifact or non-artifact. And we trained the model over 50 training iterations, giving it all of that data. We evaluated it with a pretty rigorous cross-validation schedule where each cross-validation is basically you split up your data set into different chunks and you train on some of those chunks and test on the others. We made sure to isolate pulses from each of the individual patients into each of the different cross-validation splits. So when we performed our initial evaluations, we were 100%, we were effectively training the model testing the model as if it had never seen any of those patients before. And the model performed pretty impressively on the initial training data set we used.
The reason I ask is because both the SAE and the ResNet model were trained using data from Precise Cap, which is post-cardiac arrest. And then in this case, we've tested it on TBI. So that shows the ability of these models to translate across disease types, which is nice.
That's also something that is somewhat surprising, I guess.
Yeah.
Any other questions?
Very cool. There's a few questions in the Q&A. First, are those slides? So this is, of course, from your teammate wanting to know how you did the slides inside the Jupyter notebook.
They are in Jupyter notebooks. There's a plugin called Rise that you can use to turn the notebook into a presentation. It's very convenient.
Cool. You can share that with the rest of the team. So another question in the chat. Have you considered the heuristics in the signal abnormality index paper by Sun Sun et al. In 2006?
We haven't. So far, we've just evaluated that set of 4 heuristics, but we've been looking at using signal quality indicators, using different signal quality indicators to augment that set of initial heuristics. And I think that'd be another interesting direction we could do for future work.
I quickly looked at that paper, and a few of them are similar to the ones we've implemented, but we haven't implemented the features, those specific features. But they're so simple that it'll probably make sense for us to just add them in and reevaluate, and then reference that paper. So thank you for bringing that up.
Thanks very much. Cool.
The data set is not currently available. We're still working on finalizing some of the details for publication.
Cool.
Next step, I think one of the next steps is going to be kind of evaluating a couple of different models. I still think there is room to improve the performance of these models. And one thing I'm very interested in is testing the models over a larger amount of data. So in practice, we're going to want to use these models to clean hundreds of hours of neuromonitoring data. So we need to make sure that when you give it 300 or 400 pulses from a patient, it actually performs consistently across that entire set of pulses. So I think evaluating the model on more challenging data sets and trying out different variations of these architectures and different variations specifically for transfer learning would be a very interesting next step.
And in the beginning of the presentation, you mentioned that sensitivity is the most important. And I think when we were doing the model comparison, that ends up being the weakest parameter. So we have to figure out how to improve that, because it's better for us to remove more data because we think it's artifact than miss the artifacts. Because we're dealing with so much data, we can remove more than we actually need to, which is fine. Thanks, Cooper.
So kind of a related question. So could this be then taken to other modality waveform types? And if as long as we had the set of labeled images, could we do this for others as well?
I think so. I think you would probably need to do some optimization for the exact parameters of the model, but I think this shows that this approach can work for waveform data. So I think I'd be interested to see how this performs on other waveforms like ECG, for example.
Yeah. Someone in the chat mentioned EEG. That would be the most crazy complicated one. That would probably be really difficult, but I can see more simpler waveforms being applied. Another question, can you expand on the pulse detection? Oh, you can see these questions. Can you expand on the pulse detection algorithm and the parameter of 0.4 seconds that you mentioned?
So the 0.4 seconds was kind of determined empirically by testing our pulse segmentation on a lot of different pulses. Based on the data set that we're using, that seemed to do the best job of identifying the individual pulses in the data set. So we kind of figured it out empirically by testing a bunch of different values there. The rest of the pulse detection is fairly standard. We're using kind of the out of the box find peaks algorithm from SciPy, but that method seems to work pretty well for the data set that we're using currently. If we switch over to using something like EEG, we probably would need to use a more optimized segmentation algorithm than that.
Thank you. There was another question from Jeanette. She asked how we can continue with this project, and Tony touched on it a bit in replying to how we can improve the model. I do long term, I think these models can be used to automatically annotate data as it's collected. So if we're collecting data from patient monitors or ICP monitors, we could automatically label it in terms of and leave these signal quality indicators that could either be displayed on a monitor or just be hidden and used downstream for removing bad data from analysis. I think previous systems have implemented simple thresholds to indicate when something is good or bad data, but this will be a lot more reliable way of catching those intermediate or hard to distinguish artifacts that Tony was showing early in the presentation. So I think it's really exciting to have this algorithms like these develop so that we can bring it into a system that will make it easier for us to identify what data can or should be used and should not be used.
It's always like question number 2. How do we get the data? And then how do we get rid of the artifact?
Yeah. And in terms of EEG, I think there was one person who asked about EEG. The algorithms that we've implemented perform very well for pulsatile signals, things that are very repetitive or you expect to be repetitive. EEG is a little bit more of a mess, and you may have to look at things like ICA, independent component analysis. There's probably a bunch of other. I think it's a different brand of algorithms that you'd have to apply to do EEG. But in terms of like ECG, ICP, plasmography, pulse oxygenation, any other waveform that you expect to be pretty rhythmic, I think it would work very, very well. But we are interested in doing EEG artifact removal in the future.
I think one thing that would be interesting for EEG, recently there was a paper published where some team released a large foundation model trained on, I think, 1 million hours of EEG. I think trying to see if that model could be tuned for this task, since it's already seen a lot of EEG data, would be interesting.
Definitely.
Well, very cool.
Very cool.
So I'll give people, if they think of another question, in the next minute or so.
I will say that we were working on a manuscript for 2 use cases, one with the track TBI data set and one with the precise gap data set, so TBI and then post-cardiac arrest.
We used, in the original training data set, we had 30 patients, and for each of those 30 patients, we identified 30 pulses, and those were annotated by the clinicians and used for our testing.
We surprisingly didn't need that much data.
Yeah.
Surprisingly. And one comment about EEG data in clinics in Africa, and this would help us out a lot. I sent you my email, so definitely reach out to us and we can start the conversation of how we can work together. I think that'd be a really interesting use case. So thank you for bringing that up.
And thank you for joining.
Yeah, thank you for joining.
That's awesome. It's really cool to see the reach that we're having. It's very gratifying. So thanks for joining. Cool. Well, Tony, thank you so much. Really appreciate your jumping in and showing us all this stuff. We've been excited to watch you work on it, and so we're happy that you were able to share it with the broader audience.
Thank you.
Cool.
Wonderful.
Awesome. Well, if there's no more questions, everybody have a fantastic weekend, and thank you again. Yeah, and we definitely will be publishing that paper. And we will, so, if you follow any of our socials, we'll be announcing it there as soon as it's out. So, and we think this is one of many to come from Mr. Okeke. Cool. Thanks so much.
Bye, everybody.
Bye.